Good morning. My name is Dishankar. I have with me Padmanabhan. We are with HP. I've been with HP for about 10 years. Padhu has been with HP for about 7 years. I mostly worked on the block storage part, a little bit of object storage, a little bit of file, and mostly primary storage and secondary storage. And then Padhu has been on the nimble storage side, and he has been currently working on object storage. So today we're going to talk about, this is not a new topic. We have presented this before as well. We have had some other sessions as well in this topic. So basically, applying some of the AI ML model based on some of our, call home data, and how do you synthesize and characterize some of those workloads and apply that so that you can, get closer to real world applications and how the systems are actually being used, right? Like I said, this is not a new topic. We have had multiple presentations in this area, but this is an exciting area, right? A lot of things, new methodologies, new technologies are coming up, and it gives us an opportunity to always improve ourselves, basically. So this is basically a quick agenda. So we'll talk about the background. We'll talk about how we are extracting some of the important data in terms of the input parameters, how we are modeling it. We'll talk about the different models. Padhu is going to talk about some of the techniques that we have used to concatenate and stuff like that, and how we are using it, and then we can have some conclusions around that. I'm not going to spend too much time on the abstract. I kind of talked about this. Essentially, what we are trying to do is get the data from our call home or the ASUP, right, that we get from the systems that are out in the field. You extract important elements and parameters out of that and categorize them so that you can apply them in a model, train it, and get closer to the real world applications that we are really looking at. So we'll get into the details of the solution, and in the subsequent slides you will see that we are basically talking about two areas here. One is a configuration perspective, the other one is the actual workload perspective. And we have had a presentation in SNIA in 2020 where we had used a different model, and we have some results of that. Unfortunately for this model, it's still work in progress and we're still tweaking things. But the ones that I have listed here, right, that actually shows you how we have taken existing data from our ASUP and really categorized it and be closer to what the real applications are running. So these are some examples here I've just copied from some of the workloads that we typically see coming into our database. As you can see, it's not predictable, right? It goes up and down. We have peaks and troughs, and typically in your synthetic workloads in the lab, you always have like a flat line, right? You load it up, even if you go through the different block sizes, the type of reads and writes, you still have a predictable line in a curve that you see, right? But this is actually how we are seeing customers' data that come in terms of the workloads that are being used. There's just some examples, not exhaustive. So this is the pictorial view of what we are trying to do, and we will get into the details of each of these when we, in the subsequent slides. So like you see, right, so we have the data that is coming into our ASUP repository. These are all the systems that are out in the field. And from that, we categorize it into two areas. One is basically the configuration aspects in terms of, the volume count, the volume size, and all of that. And then there is the workload aspect where we talk about the different reads, writes, and I'll get into the details of those. That's a time series graph actually. So let's talk about the configuration first, right? So mostly we are looking at the count, the size, the cache, the app aware settings, the dedupe ratios, the compression ratios, the consistency groups, the snapshot schedules, replication. So these are the data that we are actually mining from our ASUP data. And in terms of the workload, like I said, this is a time series format that we're capturing. We basically capture the histogram of the block sizes, the range of latencies, reads, writes, sequential, random, partial, background operations like volume copy and stuff like that. Then you also have the, the deletion, replication, garbage collections where you typically reclaim space, you reclaim some of the memory and all of that, and special operations like the write same, write zeros, unmaps, the cache usage, memory usage, and so on. So once we have captured all of this, right, so the configuration aspect, right, kind of goes through a config generator. Yeah.
What do you do to capture the customer array?
Yeah. So there is something called a call home or ASUP where the systems basically dump some of the stats, right, into our ASUP database. That's hosted at HP. I forgot to repeat the question. Sorry. Okay, so like I said, there are two parts. One is the config generator, which we are basically catering to the sweet spots, like it's a large config, medium config, low config, so that you can cater to a large plethora of customers. On the AI model as well, we have kind of categorized into low, mid, high range, depending on the array models, and we will get into the details of that. So that basically goes through the training, the analysis. We load that on our test system, run it through an iterative process, and really basically figure out whether it is matching to what we see from the data that is coming into the field, right? And that is saved, and we'll get into the details of that. So with that, I'll hand over to Paddu. He will take us through the different output models and the models that we are using.
Hey, good morning, everyone. So before going to the model, I'd like to touch upon few things in this. So as we define, we categorize them into workload parameters and the configuration parameters, right? So the AML part, which we propose, the model which we propose is mainly for the workload analysis phase. For the configuration, what we do is we take all the data, especially all this relevant data from the ASUP autosupport, and then we have a small script which parses those logs and gives us a configuration, like how many volumes we need to create, what is the cache settings, and should DD be enabled for those volumes, or encryption should be enabled or not. So we have those settings in place, and we generate a script out of it, and we feed that to the test array. So that's how the configuration part works. So going to the workload parameters, as Dee explained, we have a plethora range of parameters, especially all these are kind of a per second interval time series data, which we call it as a sensor or stats data, and we store them every second from the array. So depending on because since this is a per second data and we have thousands of parameters, thousands of sensors which we are capturing, it might blow out the space for the autosupport. So we carefully choose what we want to capture and what we should not capture. For example, let's say, but all those data will be there in the customer array. And for example, if we hit some crashes or some customer issue, the autosupport which gets collected because of that event will have a lot more sensor data than the regular day-to-day autosupport data. Okay, so that is one of the main differences. So we get a lot more data with those escalations or customer issues, basically. So to go through the spectrum of data, what we have, we collect from a total IO on a per second, for this particular second at this instance, how much IOs is coming into the system. And then we also get the numbers of those IOs, basically how much of that is reads and writes, and how much of them is categorized into sequential or random. So we have a sequentiality detection and random detection for the incoming IOs. And based on that, we categorize those IOs into that sequential versus random load. And also we have the partial blocks detector, which detects basically if the IO is fully aligned or if it's an unaligned IO. And if it is unaligned, we have multiple types of unalignments. basically aligning to the block, like at what offset and those kind of things. So based on that, we categorize them into 5 different unaligned IOs. So we capture all of those data per second for any given at any given point of time for the customer array. Yeah.
Do you capture anything related to locality? So where the write are going or where the read are going?
Yes, we do have that one, but we haven't considered that for our model here, but we do have that information. Yes. So once we have this histogram of blocks, and then we also have the histogram of latencies corresponding to those block ranges, all we get is a time series data out of that sensor stats, right? So we capture all of them. Along with that, we also capture some of the system background operations. Say, for example, because these background operations are sometimes which are more critical when we are trying to reproduce the issue, which eventually we will miss out and we cannot find out because customers may not say what is happening in the array. And these informations will give us like what exactly is happening in the array, especially the if we have like aggressive caching enabled and we have a lot of reads happening from the cache. So those background cache sensors will give us those details. And also if there is some deletions, like customer has deleted some huge backup volume or something, and if those deletions are happening in the background, so we will get those deletion sensors using the system background operations. Also the garbage collection. Yeah.
Sorry if this is obvious, but where do you measure these? Is it right before going into the kernel or Windows or whatever, or is it going to the device that you measure it?
So it's not into the device, it's basically in our file system layer, like where we have each component, like if you see the storage architecture, we have like index layer, we have the cache layer and all those things. So each of those layers are responsible for producing those sensor stats. So that way it's not like either at the protocol layer or at the end SSD layer or hard disk layer, it is in between during the data is passing. Oh, I'm sorry. So the question is like, where do we capture this stats? At the end or at the beginning? So the answer is like it's all the way through the transit phase. All right. So moving on, and then the last 2 settings, especially the memory usage. I didn't mention the CPU usage. We also collect that information, but that is like global. It is not. It's at the system wide. So it is not kind of like time series, but we do at certain specific intervals. Okay, so here is what the model output parameters will be. The model recommends us basically what is the range of block sizes we need to use, what is the combination percentage of reads versus writes, random versus sequential, and then how much partial blocks we have. I just mentioned partial blocks, but it also gives the combinations of how much unmaps and how much deletions we need to have. And then essentially the queue depth. So these are some of the parameters which will be the output of the model. And the above recommendations are related to configuration parameters are coming via the setup script. It's not coming from the model. So going deeper into what kind of model we use to train this, like we usually have like a combination of different models for different data, especially for the histogram of blocks and latencies. Since it is histogram data and we want to capture some spatial patterns, we chose the CNN layer, the convolutional neural networks. And since it is a time series, we went with the 1D, Con1D network. For especially detecting the IO patterns, like random versus sequential, reads versus writes, and also on the special operations like partial writes, unmaps, and write zeros, we use the LSTM, the long short term memory model. this is mainly because we need to capture the history of those operations happening for the past like 1 hour or few days. So we capture that temporal dependencies using this LSTM model. And then we concatenate all the models to get the required output. So how do we train the model, especially like what kind of data samples we take? As I said, like we get a per second sensor stats, right? So we take that for a 1 hour duration, and all those samples, like 5 different variations of block samples, histogram samples, and then the special IOs, reads SSI, categorical IOs, all those things we have per second data, and we generate a matrix for like 1 hour, which is like we'll get around like 3600 samples for an hour, and we give that as one sample input for the model. So it is like a hourly basis. We get that one sample which has that collection of data, and that is the input to the model, and the output will be like for that 1 hour what are all our IO recommendations coming from the model, and then the especially the configuration part is static, so we don't need to talk about that. But for each of that hour, the model recommends us like what all the parameters it gives.
What do you do with these recommendations? What do you do with them?
Oh yeah, so I can explain to them. So the question is, what do you do with the recommended output? So the objective of this main use case is like today, when some customer issues happens, or if you want to do some POC, which customer has done, and we could not reproduce that in our test labs, especially the dev and QA, like we go here and there like to find and ask with the customer, say what kind of workloads you use, how to reproduce that issue. So reproducing an issue is a kind of a challenge today, and it is time consuming. Even though we get all the information from the customer, it is very time consuming, because we missed at certain parameters and we could not reproduce the data, or we could not use the exact same IO patterns, which we cannot arrive at the same exact IO patterns which the customer arrived at, right? So this model recommends those critical IO parameters which we can use it in our generic IO tools like VDbench or DT or any other block IO tools. So hope I answered your question, but we'll go through that, like I'll show you how we are doing that. All right. Moving on to the next one. So this is like diving deep into the code. I kind of like truncated some of the codes because I just don't give like all the information. But if you see like this, the gist of that, like we use the TensorFlow Keras to for our model. And then as you see, like the inputs are like a histogram of blocks, latencies, and the load inputs. The load inputs especially are the background operations running, and then random and sequential data inputs, and the partial writes plus other informations like unmaps and zeros. So those goes into the last parameter. So the shape of those inputs are all like basically number of time steps. The number of time steps is 3600 here, because we are taking per second interval for 1 hour. And then the number of bins, it can vary. Today we have like the number of bins for histogram as like 5 different ranges. Similarly for latency, and for load we have like six parameters which we considered. Those are all the features what I am saying. The 6 is the features basically. And then for random sequential it is 1, and partial writes and other IOs it is basically 6. So moving on. So here is what we have, those model layers. Essentially for the histogram we use the con1d, and I use the filter size of 32. So we do like 32 times of conventional like pass-throughs, and then the kernel size is 3. The end activation function is ReLU. So we went with ReLU because that's the standards most of the time we use for convolutional neural networks. And then since this is not like a end output, so we pass this again to a concatenate model, and then we go the final layer will will have again a kind of a ReLU function. So similar approach we took for the latencies also, and since it is like 5 bins, we take like 32 filters and kernel size as 3. For the load parameters, you can see we use the LSTM model function, and we use the units as 64, and similarly the output will be like kind of like 64 outputs coming from the LSTM model for the load. So one thing with respect to this LSTM, why we went through this LSTM is because we want to remember, because if you see the LSTM is a RNN network, recurring neural network, and it kind of has a memory to it, like it can remember what has happened previously, and this is mainly used in language models, especially today, because it has to go and see like history, what exactly spoken previously, right? So all these load parameters, we need to know like what happened exactly 1 hour back or something. So that gives us the history, and that history is captured in this LSTM model. And that is one of the reason we went through it. And similarly for IO types, essentially like random versus sequential, and then detecting all the special IOs, we use the LSTM network. And then we concatenate all of them and pass on to the dense layer, which is 128 neurons, and then we pass on to another dense layer, which is 64. So this is our model layers, and then once we have these models, we define the output parameters. The output parameters are essentially the range of blocks, the range of latencies, what we get, and then the IO counts. The IO counts will give the predicted number of reads versus writes, and then the IO types, it gives the probabilities of 4 different IOs, essentially whether it is a partial rates, whether it is unmaps, or whether it is write zeros, those kind of thing. And then we have so that is the last one which I mentioned. And then we have the IO types, which gives like sequential versus random, and reads versus writes, those things. So then we build the model using keras.model, and we feed in the inputs and the outputs which we defined. Once we have that, we compile it. So while compiling, we use the standard Adam optimizer, and for loss and matrices, for each of those for input features, we use different loss function and the matrix function, especially for blocks, latencies, and IO count. We use the mean square because it involves a lot of numbers, and especially with IO types and detecting the partials and unmaps, all categorizing, we use the categorical cross entropy loss function, and same for matrices as well. So once we have the model compiled, we can go and fit it. So the inputs, if you see, like it's all like the histogram sensor data, time series data, and then the output is like block ranges, latency ranges, and all those things. And we train this for certain number of epochs. Actually, we did it for like 10K, and then with batch size of like 1 hour batch size, which is 3600. And then the entire data, actually, we split it into kind of like 80-20. So 20 is for test and validation. And then we go to the evaluating the model. So we pass on to the test data, which we partitioned, like the 20% of the data, and we test it. So this is our entire model, how we train and evaluate them. Especially in the training phase, to get those data, what we did is we used customer ASUP data, but in that one we don't know what is Y actually, what is the exact workload recommendation. So what we did is we used the known parameters using our known IO tools from VDbench or DT IO tools, the regular IO tools, and then we generated all our time series data. So we use that as a model training data. So that way we know, we exactly know what is X and what is Y. Also similarly, for each of the features when we are testing, we included those feature specific data for training. So that way the model is trained with those particular features. Example, if the workload is involved mostly into deletions or mostly into unmaps, so we need to have that information fed in with specific sensor data information, right? So we cater to all those different feature workloads and train the model. So once we have that, so this is a kind of like a output we use, like this is the kind of input we give for the VD bench or any of the IO tool. Essentially all the critical IO parameters, like what are the block sizes, what is the queue depth, and how much is the dedupe units, dedupe savings you need, what is the compression ratio you need. So all these parameters which we get from the IO tool, from the model recommendation plus the configuration script, we combine them and feed into the IO tool. This is essentially another kind of a system. What we do is basically once we generate this information, which is like more like a workload parameters, today if someone finds that workloads, they go and execute it and they forget it. Let's say for after 2 years, same issue happens, so kind of similar signature, and it's pretty hard to come back and remember what exactly the workloads we used. So to cater that, what we did is like we feed in those models with a specific label names like the customer escalation number or the feature what we are dealing with. Say for example, if it's a deletion or GC heavy loads, we added the label for that one and we feed into the Elasticsearch database so that it can be referred later and easily accessible for any of them who is searching for that workload. So this is kind of like an interface with the front end and the back end is Elasticsearch. We created a UI where we can feed in all these workloads, store it in the Elasticsearch with the proper labels. And then there is also another UI where you can go and by single click you can execute that workloads in the array. So all those information is stored in that entity, one Elasticsearch entity, and with proper labels, and then we can, like anyone in the company, they can go and search for it and take that and use it for their workloads or for reproducing the issue.
I'm not sure I got it, but will you leave it running all the time? What is is the override too much or not? For example, you could leave the gathering running all the time, and when you have a problem, and you keep on with the last power. So when you have a problem, you have the last power gathering.
So your question is like, do we keep running the workload or we just stop it?
Not the workload. I'm talking about when the customer is using the system. And for example, you could turn on all the gathering of the data and let it run always all the time. So is it too much override?
Oh no, actually, so these data, it's anyway collected as a part of the feature or functionality in the customer array, but it is not sent to us during the peak hours. So the ASUP data is sent like during midnight or sometime, or whenever the customer schedules it. And also, but whenever the event happens, like a crash or something, that is like event based ASUP data, that will be sending immediately. It will send the details immediately because we need to have a lot more per second interval data, which might go rolled over. So those information we capture faster and send it immediately once the event has completed. All right. So how frequently we revisit the model and what are the categories? Like since we have like different categories of storage array, especially like low, mid, and high end arrays, this model as a single entity cannot be used for all of them because there are a lot of variants coming in. So we used 3 different models, training for each of them separately. And when the training happens, especially when there is some new information or new escalation comes in from the field, which we don't know, we add those parameters as a part of training, especially the sensor data. And also, for example, any new features or new testing happening in our lab, so we use that information as well to train the model. So that's all. I think the conclusion is like, so this approach is not new, but adding the deep learning part to it and getting those from the model recommendations is kind of something new which we tried. And then this also helps us to be closer to the real world workloads rather than using a synthetic workload from someone like thinking like, okay, this might probably reproduce the issue. There is no assumptions kind of thing, so it's all like a feedback mechanism we get from the model. And this also helps us to get to the customer issue faster, like reproducing the issues. And at least, like, I would not say we haven't we came very close to the customer kind of like load generation, but it's like kind of definitely a differentiation factor from what we do with the synthetic workload versus using this model. Yeah, I think that's all from the slides. Questions? Yep.
In customer identified issues which were successfully replicated, can you give us a sense of the correlation of what the customer was running to what the synthetic replication was closer to 80-90% or very accurate?
Yeah, the question is like how accurate is this model, like with respect to customer issues versus like how you reproduce, right? So we haven't, as we said, like this model is still it's like in development phase, so we haven't tested it completely, but we are pretty close. We are getting around like 80 to 85% of accuracy at this time, but we still need to give some manual inputs, basically like see like what's the other unique things which the customer does, because there is always a new factor in any of the customer issues, right? So we take that and feed in still.
And the previous model that the other example that we did, right, we did achieve about 85%. But what is happening is our systems are also evolving, right? We have more sensor data now in terms of some of the different layers that you have. We are getting more sensor data. So the whole idea is you are able to improve on what we already have, and we are hoping that it will be better than this.
Yep. Yeah.
So I understand that you use this more as kind of part of your testing environment. Is it something that is used also to improve support for customers, and if you detect that the behavior of particular customers is different than anybody else?
So the question is, can this be used by customers also to?
But like by customers directly, or at least by customer support within your organization?
Yes, so we do give feedback recurringly to the customer support, so they are aware of any of the issues which we newly defined or we came to know in the lab environment.
So this particular one is still work in progress, but the previous one, which we did in 2020, that already the customer support folks are aware, right? And some of the demos and all that typically do, right? They will take a sample of that and run and say that this is an actual workload that is being run. So that aspect.
You're not audible.
Okay. Sorry, you had a question.
Yes. So if you could run this workload characterization live on the array, assuming it was cheap, would there be any usefulness in this information, like tune the array in some way to increase performance or save energy? Have you thought of any other use cases apart from replaying the workload essentially?
So the question is like, can we use this to play it live in the array and
Make decisions.
Some other
make decisions?
and
Yes,
use cases.
definitely. I think we can do it. So this can be mostly useful in some of the POCs, like where we want to show to the customers, instead of like synthetic workloads, we can show like the actual use case workloads. And we can quote like, okay, these are all the escalations came out and the workloads has been derived from this customer issues, and we are like using that workload kind of thing. Essentially, since we have the system to tag those workloads and store them and retrieve and play them at any time, so we can use them for the performance tuning as well as for other improvements as well.
Yeah, for the performance improvements, we are definitely using it. See, there are two parts to performance, right? One is your like this SPC numbers that you present versus your feature performance, right? So this is mostly what we use is in terms of the feature performance, right? If you're taking a lot of snapshots in the background, right, and at the same time you have certain level of workload going on, right? What are the expected parameters that you would see typically when you go through, say, maybe a IOStack restart, user space restart, or something like that, right? So that aspect is what we kind of look at. But from a pure performance number, that is outside of this purview. We haven't explored or thought about that.
In terms of data capture size, how big is this data?
Yeah, so we have seen, as I said, like this event triggered auto support data, it's kind of like bit larger and it takes time for us to reach as well, because from the customer array, whenever the event happens, it triggers immediately and then it sends that data in batches to our InfoSec team. But the regular ASUP data, which is happening like every midnight, it's a kind of like very short. I would say probably. I'm not sure about the exact size, but it's
20 to 30 GB.
not in GBs, probably in MBs.
No, the crashes when.
Oh yeah. The crashes has like GB because it has cores and everything, but others it's probably in 1 GB, less than
it's
1 GB.
every day, right? So it's basically the delta that is sent.
Yeah.
So that's not much.
So you mentioned three different types of storage systems, like three different models. So what are the characteristics of those storage systems in terms of like SSDs and
Yes.
Exactly.
Yeah, good question. So the question is like, how do you categorize the storage system, like low end, mid range, and high end? So essentially, it has many parameters to categorize them. Essentially, the CPU, memory, and then the load, especially how much SSDs the capacity it can provide. Also, how much cache settings if it is a hybrid, like what are the cache capacity for that. So those are the parameters categorizing them.
Is there like a product categorization?
Yes. So we do actually, as a part of HP Nimble solution, we do have like a hybrid and all flash arrays, and within them we have like different models based on the CPU, memory, and the hard disk capacity. Yes.
Have you guys thought about, is this open source?
Uh,
Or thought about open sourcing it? Is it possible? Like, can you speak about
Yeah, as I can. So the sensor data, what we have, it's all proprietary. It's not open source. So unfortunately, that's why I could not give those data like exactly like samples and stuffs. But this model essentially, it's just it's a convolutional neural network and RNN, right? So it is widely used everywhere in the industry. So this can be definitely used by anyone.
and how about the way you extract the data? That's also.
Oh yes, that's proprietary. The way we extract the data, especially the auto support data, it's all proprietary. Yeah, so we cannot share that.
And sorry, just last question about that. Do you think having, because okay, you developed it for a very specific deployment. How difficult do you think it would be to have an open source general version of it, where, for example, it could, run on somebody having ROXDB, somebody having CacheLib, or somebody having whatever, somebody having your product, and getting those data and having exactly the same results? Is this like?
Yeah, it can be done, provided we get all those input parameters similar to what we have in this model. Essentially, if you see the input parameters here are especially like what is the block size we use, and that is given by most of the IO vendors today, like the storage vendors today. And then what is the latency? It is available for anyone if you see into the dashboard. Then
if you tweak the input parameters, right? And cater the model to basically extract that, and
we should be able to do it.
Yeah.
Okay, let's see. I think we are on time. Yeah. Thanks everyone.
Thank you.
Have a good day.